Okay, welcome back to the second part of paintings, polygons, and plant propagation. So the HillClimber, it takes one mutation, one of those 4 mutations we saw, and if it improves, it keeps it, and otherwise it reverts. And simulated annealing can also accept these bad mutations, depending on the size of the worsening of the deterioration and the temperature that usually declines. So the chance of accepting larger deteriorated mutations goes down through time. And that's the whole idea of simulated annealing. And thereby it can go back from local maxima by first deteriorating and then improving again. And now the third heuristic algorithm we used is different from the other two, in that it uses a population of solutions. So HillClimber takes one solution, an initial constellation, mutates, getting better. Simulated annealing, mutates, getting better, getting slightly worse, getting better, getting worse, getting better, etc. But plant propagation has a number of constellations. And I'm gonna, first, this is Abdel Salhi, and this is Eric Fraga, and those guys invented this algorithm. So basically what you do is you have these populations of, you have a population of polygon constellations in this case, or in some other problems, traveling salesman routes or university timetables, or in our case, a population of polygon constellations. And the first thing we do is we rank them to fitness. So the one with the lowest MSE or the highest fitness, the best approximation, the best solution, goes to the top of the population. And the worst approximation goes to the bottom of the population. I'll have pictures in a moment, right? The fitnesses are then scaled to between 1 on top and 0 at the bottom, and they're somewhat smoothed by a tangent function, a hyperbolical tangent, here it is. And the key idea of plant propagation is that those fittest individuals, they produce a lot of offspring with very small mutations. And the unfittest individuals in the population produce very few offspring with large mutations, right? And then you produce a number of offspring, and you kill them off until you have a new population site of the best individuals. And this is what it looks like. So here we have a population of a relatively good approximation, somewhat worse, still worse, and terrible. Well, not terrible, but not definitely bad. And what the first, what the best individual does is it makes a lot of new offspring, all with very, very small mutations. Some are slightly better than this one, some are slightly worse. Number 2 makes slightly fewer offspring, only 3 in this case, with slightly larger mutations. Some are a little bit better, some are a little bit worse. Number 3 makes still fewer offspring with larger mutations, and one of them is actually very, very bad, as you can see. And number 4 makes the fewest, is that the word? The fewest number of offspring, only 1 in this case, with a lot of mutations, in this case, leading to a very bad approximation. And then what happens is our population size was originally 4. We have a great number of offspring now. We need to go back to 4. So what we do is we mark the 4 best approximations out of the entire expanded population, and the rest, look at that animation, isn't that great, is being killed off, right? And that is one generation of the plant propagation algorithm. So in the next generation, these 4 will be ranked, and the whole process will restart, making new offspring, etc., 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 generation after generation after generation. So for the original investigation, we used 7 paintings. We used 3 algorithms, the 3 that we just discussed, 6 vertex numbers, and 5 runs of 10 to the power 6 to 1 million evaluations. And that is important, because otherwise you would have, you need to test by evaluations, because the plant propagation algorithm produces a lot of new offspring every generation. Whereas the HillClimber and the simulated annealing operate on just one individual that keeps improving. So you need to take those evaluations, because otherwise the plant propagation will always be the better algorithm, because it does so much production. So that's why we count evaluations. MSE, so the quality of the approximation, is one evaluation, and therefore the number of generations of the plant propagation algorithm is smaller than the number of iterations from a HillClimber. Right? Always compare evaluations. So let's have a look at one of the algorithms. I believe this is the HillClimber. But if you would do something like this for plant propagation, you would always shoot the best individual for each generation. Oh, there we go again. So that's how the algorithms operate in a visualized way. So let's have a look at some results. So generally speaking, and this is very interesting, the HillClimber produced the best results. Yes. So even though it is prone to getting stuck in these local optima, it produced the best results for nearly all paintings. We would expect to simulated annealing to perform better, but it really performed really poorly, and that might possibly be due to bad parameterization, and we solved that later. I have a remark on that. And then we have plant propagation, and it performed worse than HillClimber, but it still performed fairly decent. But this was the ranking in quality of the approximation. And you can also see it here. The lower the MSE, the better the approximation. And for the HillClimber, you can see that after 1 million evaluations, that it really drops lower in its MSE than plant propagation for a great number of vertices. It almost always outperforms plant propagation. And I've skipped simulated annealing completely because it was so bad. So how come that the plant propagation algorithm is actually outperformed by the HillClimber? And I have just one explanation, and it comes from a different paper, a paper by Gelijn van der Meer van de Post de Berg. And it's about the university timetabling problem. And in the university timetabling problem, also a HillClimber was used in 2 different versions of plant propagation. And it really took us a long time to see that plant propagation actually outperforms the HillClimber as expected, but only after a very, very long time. Yes, because it produces so much offspring. And this is a relatively common phenomenon, or at least previously witnessed, and described by Ivan and Smith as a tortoise and hare situation. So a HillClimber gets really, really good results really fast, but it gets overtaken by more elaborate algorithms, such as, in this case, the plant propagation algorithm. We think this also applies to paintings from polygons, but we still have to see. So, and then about simulated annealing, and this is work by Redouan Dahmani, Anne Meijs, and Sven Boogmans, who actually took a different, this is the original really bad performing cooling schedule for simulated annealing. And what Redouan did actually was just take 9 really different cooling schedules for simulated annealing, and the redness indicates the relative average temperature of a cooling schedule. So this was the hottest, and this was the coolest, and this was something in between. And the really interesting thing that we saw is that it really makes a really big difference which cooling schedule you use for simulated annealing. This is one cooling schedule over here, the end result. Really cool cooling schedule, and this is much warmer, and you can see that the result is much worse. So simulated annealing just failed because of poor parameters. Plant propagation probably failed because the time was simply too short. Okay, so to everyone seeing this video, I would like to challenge you. If you can make better approximations than us or outperform our algorithms, that is very good. We'd like to see it. And either submit your works to some conference or get in touch with me, and throw your comments in the comments on YouTube, or contact me via social media or whatever, by email. Right. So this is the end of the meeting. This is the end of the presentation, of the video. Thank you very much for watching. Anything you have to remark or question, please just throw it in the comments. Bye.